let's learn about a special case of factoring. These two cases that we're going to learn today are GCF and difference of squares. I want to remind you, though, that the box works for every bit of factoring that you would want to try. All right, so here are some examples. I'm actually going to start with a linear example. All right, so the expression 10x minus 25. All right, this expression can be written as a product, so it can be factored as well. So you'll notice we can do GCF even without a quadratic. So the concept of GCF means that you look at each term and you see if they have a common factor. So is there any common factors between 10 and 25? You know, obviously a 25 doesn't have an x, so x is not common, but is there a number that'll fit into both 10 and 25? And if there is, can you find the largest one that will do so? So the largest number that does that is 5. All right, so that's why it's called greatest common factor, 5. And what you do is you factor out of 5 and you write your second factor. So 5 times 2x will give me 10x, and 5 times negative 5 will give me 25. So the factored version of that is 5 times 2x minus 25. In other words, when you're factoring by GCF, you're extracting a monomial instead of breaking this up into binomial times binomial. So 5 is a monomial; it's one term. Okay, so that's one example. All right, another one that you could try. Let's take a look. Another one that you could try. Well, let's get to quadratics now. You'll often see quadratics like this: 8x squared plus 3x. All right, that are lacking a c value. All right, and it doesn't mean that you only do this when it doesn't have a c value, but this is common. So what is a number that'll fit into both 8 and 3? Well, the largest one is 1. Right, so you can say 1, or you could not write anything at all. And the largest variable that fits into x squared and the x is x. So this is 1x multiplied by, well, we'd multiply this by 8x, and we would add 3. All right, so we will get x times 8x plus 3. X times 8x plus 3 is the factored version of 8x squared plus 3x. It would have been nice if the 8 and the 3 would have had, or the coefficients would have had something in common. All right. Continuing. So let's do an example where they do have something in common. So 6x squared plus 48x. 6x squared plus 48x. So 6 will go into both numbers. X will go into both x squared and x. So you factor out a 6x, and you're left with x plus 8. All right. And that's how GCF works. Now I want to remind you that this actually is consistent. It is consistent with what you've learned about the box. Okay. So a lot of times students will forget that GCF is there, and they'll kind of complicate their lives using the box, but it still works. All right. So if this is 6x squared, but then you got a 0 right here, and you need to make 48 x's out of here. So that's a little complicated, but you know that one of these is going to be 0, right? And then you're stuck kind of guessing with a lot of things missing. So that's why I think that it's better, in this case, it is better to actually use GCF, all right, to factor that. Okay. And the last thing that we're going to talk about is a difference of squares. All right, so difference of squares is whenever you have a quadratic with two perfect squares, meaning that both terms are perfect squares. So for example, 121 minus x squared. You'll notice 121 is a perfect square. X squared is always a perfect square. All right, so these actually factor to something simple like this: 11 minus x times 11 plus x. All right, another example would be x squared minus 9, and this one factors to x plus 3 times x minus 3. All right, and if we do a general case, if you have a term squared and you subtract another term squared, then that results in the first term, square root of the first term plus the square root of the second one times square root of the first one minus the square root of the second one. So that is difference of squares. And it can be further illustrated by you're missing a b value, so there are no x's right here. There's no x's. Well, there are.